Welcome back to a favorite channel Science with Mukherjee sir. Myself KT Mukherjee. Today we are going to discuss a very important topic in haloarenes and haloalkanes. In this video we are going to discuss the stereochemistry of the Sn1 and Sn2 reactions. So today's video we are going to discuss the stereochemistry of the Sn1 and Sn2 reactions. Sn2 reaction proceeds with the complete inversion of the stereochemical structures. So we can write the Sn2 reaction is basically relates to the complete inversion. Relates to complete inversion of the structure. Complete inversion. Whereas the Sn1 reaction proceeds with racemic mixture. So these two things happened when the Sn1 and Sn2 nucleophilic substitution reaction occurs, and this we will going to discuss in detail how this has happened in these two reaction mechanisms. For this, first we need to know some very fundamental things. So we are going to discuss this because this relates to the optical activity of the compounds. Now, what is optical activity? Optical activity is basically a special characteristics of a compound. When the solution of the compound we pass some PPA, plane polarized light. Plane polarized light. When we pass the plane polarized light, what is plane polarized light? PPL. It is basically the ordinary light when pass through the nickel prism. When the ordinary light has been passed through the nickel prism, it becomes the PPL. The solution of the compounds which rotate this PPL, we will call this is optically active compound, and this phenomena is called the optical activity. Polarimeter is one of the equipment. Polarimeter is the equipment by which we can able to measure the degree of the rotation of the plane polarized light by the solution of the compound. When the compound rotates in the positive direction, it is called the dextrorotator. So rotation in the clockwise direction is called dextrorotator. And it is being designated as D, and it is plus is being given in front of your the degree of rotation. And the rotation in the anti-clockwise direction, it is called the levorotatory, and it is being designated as L, and this is the minus. So this is the the compound having this type of plus and minus compound is called the optical isomers. This is called the optical isomers, and the phenomena by which we can able to see this type of things, that same compound will having the same molecular formula, having this everything is same, but same compound sometimes it shows a positive direction rotation of the plane polarized light, and sometimes it is shown the negative direction rotation of the plane polarized light. We will call this is the optical isomer, and this phenomena is optical isomerism. Now question arises, why it is being shown by the compound, what is the reason behind it? And after a detailed analysis and discussion, it has been observed this is because of the asymmetry. Structure of the compounds is responsible for this optical isomers. As for example, for the organic compounds, it is been seen when the carbon atom is joined by 4 different groups or 4 different atoms, it has been called the carbon atom is asymmetric, and accordingly is shows the asymmetricity in the compound itself, and those compound is going to show the stereoisomerism, and it is also called stereocenters. And these compounds have been seen that this has not the imposable mirror images. So this is the asymmetricity of the compound that shows the optical isomerism, the optical activity of the compound. And this can be said that this type of compound do not have the mirror image which can be superimposed. These compounds will have the non-superimposable mirror images. As for example, we can this is a structure of the 2-bromopropane. Here you can see the CH3 hydrogen and bromine. Means all the groups attached to the carbon atom is not the same. All the groups, that is CH3, that is all the groups should be present, that will be different, but here you can see all the groups attached to the carbon atom, that is have the similar type, that is has 2 CH3 group. This type of compound having the superimposable mirror images. This type of compound, superimposable mirror images, that you can easily understand from this discussion. That is, this is the mirror image of this product. When we are going to superimpose the mirror image, we have to rotate this mirror image by 180 degree. That is the convention, that is the rule. So when we rotate this, what we will find? By 80 degree, 180 degree, what we will find that it is become now we can see this and this can be easily superimposed because both the group joined here is CH3 group. That is why this compound will not going to show the optical activity, and this compound is called the achiral compound. Achiral because the carbon atom is not asymmetric. This is called the achiral compound, and this is do not show the optical activity. These do not going to show the optical activity. But this compound, 2 bromobutane, that you can see here you can see 2-bromobutane, the carbon atom is joined to the C2H5, CH3, H, hydrogen and bromine. All the groups or atom is defined. So this carbon atom we can say the chiral carbon atom, and it is a symmetric molecule. So when we make a So when this is the mirror image of this, and when we are going to superimpose this mirror image, we have to rotate this by 180 degree, and we have rotate this. So what we find, this is the mirror image, and if we want to superimpose this mirror image, we are going to get the different picture of it. What is that? Now you can see that so when we rotate 180 degree, what we get? We get that C2H5 is below the plane of the paper and CH3 above the plane of the paper. But here you can see C2H5 above the plane of the paper and CH3 below the plane of the paper, and that is totally different. So these two structure will not going to be superimposable. So this compound is going to show the optical activity. So now we understand that optical activity is basically related to the asymmetry of the molecules, and the carbon atom will have, if it is having the different atoms of different group, and it will going to show the optical activity. Now we are going to discuss how it is correlates with the stereochemistry of the Sn1 and Sn2 reactions. This is a 2-bromooctane and it will show the Sn2 reactions mechanism while we are going to react with this hydroxyl OH group, and it will going to produce that. We know for the Sn2 reactions, when there is a Sn2 reaction, what is going to happen? The OH minus, here the nucleophile will attach to the opposite of the halogen atom. It will attach to the opposite of the halogen atom. So there will be the complete inversion of this structure, stereochemical structure. So it will be like this. This will going to produce the octane 2-ol. But this octane 2-ol, this is a minus. This is the, as per optical activity constant, it is a minus 2-bromobutane, 2-bromooctane, and it is going to produce the plus octane 2-ol. So you can see that this compound was previously, before the reaction, it was the minus optical, that is your radiorotatory. Now this has been changed to this octane 2-ol as a plus. So there is a complete inversion of this product after the Sn2 reaction. Now the Sn1 reaction proceeds. In the Sn1 reaction, we know that is basically We know Sn1 reaction, as for example, 2 bromobutane. 2 bromobutane. Here, the structure of this compound is like this. This is the 2 bromobutane. For the Sn1 mechanism, what we see, this will have the 2 steps. In the first steps that you can see the production of the carbocation. This is the production of the carbon atom. Now, and this carbon atom is sp2 hybridized. And now when there is an addition of the OH minus, it can be the OH minus, OH can be added to at that position where initially there is the halide ion, bromine atom. It can, when it will add to this position, then there will be complete retention of their configuration. If it adds opposite to this bromine ion, because the OH minus ion can be added in both the directions. In the both directions. So you can see this is the bromine atom attached initially. So if it attached here, so it will show the same configuration as the so this will minus sign and minus sign, and it is, if it is opposite of this, and it will have the different structure. So in this case, the structure is totally different. That is a complete inversion of the structure here, and here the retention of the structure here. So this is the, if it is a minus, then it will be the plus. Optically, it will rotate the in the positive direction, the clockwise direction, whereas it can rotate the negative direction or the negative directions. So this will create a, we have 50% of this compound, optically active compound, and 50% of this different is enantiomers. Then it will create a racemic mixture. So we can understand how that in the Sn2 reaction, there is Sn1 reaction, there is a racemic mixture. 50% of this optically active which radiorotatory and 50% 50% extrarotatory and 50% regularotatory, and both are rotation will be cancelled out by each other, and it will going to give a product which do not have any optical activity, and their optical activity do not observe the optical activity in this compound, in this product. So now you can understand how in the Sn1 and the Sn2 reactions the stereochemistry changes due to the different type of the addition of the OH minus ions nucleophile at the same time, and that is going to give a very interesting things. And in case of Sn2 you will find that is a complete inversion. In case of Sn1 that proceeds with the racemisation, where you can see the 50% of this product having the different rotation and 50% product having the other rotation, and those rotation is being cancelled out each other. So I think this is clear to all. So this is all for today's video, and we will discuss the next video regarding the other chemical properties, that is elimination reaction and reaction with the metals. So all the best and be best.